Hello, everyone. It's me, Billy Younger, again, and this time I'm here to solve another physics problem for you. This one's kind of interesting in that it's another opportunity to convert units, but in this case, you can convert units both in the numerator and the denominator. But in doing so, we're dealing with water, so we're actually learning a little bit about water itself, which is also kind of interesting, and how much it weighs, and some fundamental units that you run into in everyday life. So it's just a problem I've always assigned to my students because of the extra learning you can get from it. So let's go ahead and share the screen and get you started on that problem. So here's the question, or here's the problem. It says, according to the groundwater manual, a water resources technical publication published by the U.S. Department of Interior's Bureau of Reclamation, the density of water, in other words, I'm just giving a citation of where I got the one to that many decimal places. The density of water at 4 degrees Celsius is 1.00000 grams per cubic centimeter. Also, it's 64, I think it's supposed to be 64 point 64.4424 pounds per cubic foot. I don't know where that figure came from. There's clearly some kind of something happened in there. I'll double check, but I'll put it red right now because I'm not sure what's going on with that. It seems like the decimal place is wrong because I'm familiar with water weighing about 62 .4 pounds per cubic foot, and I think that's the actual figure. This must have been a typo, so ignore that. This happens to be the temperature at which water has the highest density. Again, I'm referring to 4.0 degrees Celsius is the temperature at which water has the highest density. That's also allows you a little bit of a Jeopardy question if you say there's a frozen lake in northern Michigan or Wyoming or something like that, and it's completely frozen over, and they ask you what the temperature of the lake is at the very bottom, you can certainly tell them it's 4 degrees Celsius because that's when water's the actual densest, and therefore that water would be at the very bottom. So that's sort of what we're learning about here is 4 degrees Celsius is the highest density of water. And in fact, if you go higher temperature or lower temperature, it gets less dense. And in fact, of course, you all know that ice floats. So the solid form of ice is even less dense than the liquid form. Anyways, that's what I meant when I said this happens to be the temperature at which water has the highest density. By the way, in scuba courses and other places, they suggest the density of seawater is about 1,025 grams per cubic centimeter, but they usually use it in like 64.0 pounds per cubic foot, but sometimes they'll use the kilograms per cubic meter figure as well. So that's a nice little different approach to it. Also, in my scuba diving class, they had a certain number of pounds per square foot per meter was another density, which you can do that way because then if you just multiply that density, since it's pounds per square foot per meter or per foot even, then you can see, oh, okay, well, if I multiply it by the depth, then I know how much pressure or ambient pressure the water is. So what is the actual problem here? Well, part A, I want you to calculate the density of water in kilograms per cubic meter as opposed to just grams per cubic centimeter. Part B, I want you to say what is the density in grams per milliliter. Part C, I want to know what is the density in kilograms per liter. And then part D, I want to know what about in pounds per gallon? What is the density in ounces of weight divided by fluid ounces as well? So there's two parts to part D. That's really what I'm trying to get you guys to solve. And I think the results are kind of nice. So let's stop sharing this. Actually, before I do, I want to go ahead and write down some figures. So at 4.0 degrees Celsius, the density of water, and we often use the Greek letter rho for the density. So I'm writing 1.000 space 00, and that's grams per cubic centimeter. And I'm putting my strings of numbers in pods of 3, which is always good practice anyways. I do believe, like I said, that that 644.24, I think that's incorrect. I'm going to write that over here. What I'm almost certain it is the density of H2O is something like 62.4 pounds per cubic foot. And I'll put a question mark by that just to say what it is. In part A, they are wanting to know the density in kilograms per cubic meter. In part B, they want to know it in grams per milliliter. In part C, they want to know it in kilograms per liter. And then in part D, they want to know it in pounds per gallon and ounces per fluid ounce. Okay. So these are all the questions that have been answered. I've now written down the information they gave me. I've assigned symbols to the information they've given me, and I've written down the information that they're asking for, and in some sense assigned symbols to those as well. So I can stop sharing my screen, and now's probably a good time to start sharing my iPad screen. So let's do share screen, iPad. And here it is. So you can see what I've jotted down. I wrote the 4.0 degrees Celsius down. Notice I used the Greek letter rho, which looks like a P sort of with a little curvy. And of course, it doesn't have a vertical straight staff like a regular P in our alphabet does. But anyways, that's what a rho is. 1.00000 grams per cubic centimeter. And that red one is the one that I think is the correct figure for whatever that was supposed to be in the parentheses in the problem. Again, I wouldn't necessarily trust me on that. But anyways, that's what I remember from taking scuba diving back in, geez, it was 1990. So actually, no, that was 93. So that was, what, 30 years ago? Anyways, so let's work on our solution. So our solution is we are just in fact solving our converting units. I know that the density of H2O is equal to 1.00000 grams per cc. Remember, cc is another way to write cubic centimeters. I just got to remember that it means literally centimeters times centimeters times centimeters. In this first case, we're wanting to convert it to kilograms per cubic meter. So I'm going to first tackle the kilograms. So this is close enough. Normally, I would take the time to put the 1 over a 1, just so we'll know clearly that the 1 is in the numerator. But I think we're able to go ahead and take off our training wheels now. I do know that there is, in fact, 1,000 grams exactly in 1 kilogram. So that's definitely going to convert my grams to kilograms. And now I also know that there is exactly 100 centimeters in 1 meter. And of course, I don't have centimeters here. I have centimeters times centimeters times centimeters. So what I'm going to do is save a little space and write that as cubed. Now, what does that mean? What that means is I'm going to multiply the 1 that is right to the right of the equal symbol, the 1.000 space 00. I'm going to multiply that by the 1, which is a kilogram, and I'm going to multiply that by 100, then by 100, and then by 100 again, and that would give me my new numerator. And then I'm going to take the imaginary 1 that's under the 1.000 space 00, and I'll multiply that by 1,000, and then times 1 times 1 times 1, and that'd make it the new denominator. Then I'd divide the new numerator by the new denominator, and that would give me the whole answer. I'm not going to take the time to show all that. I think you've all seen it, but what I will do is remind you that cubic cc cancels out with centimeter to the cube power. So really what you can tell is I am going to multiply by 10 to the 2, which is what 100 is, raised to the third power. And when you raise a power to a power, you multiply the exponent. So 2 times 3 is 6. So that's 10 to the 6. And then I'm going to divide it by 10 to the thirds. So 10 to the 6 divided by 10 to the third. When you divide powers with the same base, you subtract the numerator's exponent, you subtract from it the denominator's exponent. So 6 minus 3 would be 3, and ultimately I get 1. Well, ultimately I get 1,000.00 kilograms per cubic meter. And that is the exact right answer for the density of water in kilograms per cubic meter. Now, it's also relevant, and this is part of the reason why I always like to do this problem. I think I got it from the textbook Wilson, Buffa, and Liu, an algebra-based textbook that I did some work for a long time ago. But they always point out that, in fact, a cubic meter of water has a mass of 1,000 kilograms. Now, if you assume you're near sea level, then gravitational acceleration is 9.8 meters per second, and you multiply that by the 1,000 kilograms, and you'll get the number of newtons. And then if you convert that newtons to pounds, you'll find that's about 2,200 pounds. That's what we call a metric ton, or a long ton, or a big ton. Okay, so that means a cubic meter of water, it literally weighs a metric ton. On the other hand, if you were just to take 1,000 pounds as opposed to 2,200, that's called a short ton, and that's the ton we normally use, and that's the tonnage they refer to when they talk about, F-150, F-250, F-350, or Chevy, uh, 1,500, 2,500, 3,500, and of course they actually go higher than that, as some people know. But anyways, I hope that helps. So we've now done part A. Part B, we'd like to convert this to grams per milliliter. And of course, to do this, we need to make use of what the milliliter is. And I actually handled that in another video. So I'm going to just remind you that 1.0 with an infinite number of zeros after a liter is defined to be 1,000 with an infinite number of zeros after it, centimeters cubed, because remember, a liter was supposed to be a 10 centimeter by 10 centimeter by 10 centimeter cube, like this. Okay, so that's actually a fact. So what we now have is we want to convert the density of water for part B to grams per per milliliter. Well, if we see that 1 liter is equal to 1,000 cubic centimeters, then 1 milliliter, which is just equal to 1 liter divided by 1,000, that's equal to 1.0 with an infinite number of bars on it, centimeters cubed. In other words, I just took that definition, 1 to an infinite number of decimal places, liter, divided by 1,000 is the definition of a milliliter. So that's why I got 1 milliliter on the left. And then that's defined to be 1,000 with an infinite number of 0 decimal places, centimeters cubed. But if I divide the left hand side by 1,000, I got to divide the right hand side by 1,000, or it's no longer equal. So in fact, what I now have is that 1 milliliter is the same thing as a cubic centimeter. So I can now say that the density of water is also equal to, instead of 1 gram per cubic centimeter, it's also equal to 1 gram per milliliter. And in doing so, we've just discovered that the cubic centimeter is equal to the milliliter, which I of course ran into when I had our first child, because inevitably one doctor will write a prescription for a certain number of cc's, and a pharmacist will write type out on the bottle a certain number of mLs, and it helps to know that 1 milliliter is the same thing as a cubic centimeter. So that's another reason I like to include this particular problem in my sets. So now let's look at problem C. Problem C, we wanted it in kilograms per liter. We already had 1,000 kilograms per cubic meter. So I'm going to start with that one. And I'm going to go ahead and put it as 1000.00 over 1. That's just to make the units or make people that aren't too good with fractions feel a little more comfortable. So here's the kilograms, here's the cubic meter. Now what we realize is that 1 liter, and we actually did this in a previous problem too, you probably know 1 cubic meter is supposed to be 1,000 liters, and that would be the easiest way to do that, but I'm not going on the assumption that you've solved that problem already. So what I'm going to do is I'm going to convert from cubic meters to cubic centimeters, and then from cubic centimeters to liters. So what I'm going to do is I'm going to say, okay, well, I happen to know that 1 meter is equal to 100 centimeters. And of course, I got to do this 3 times to get rid of the meters times the meters times the meters. So really what I'm doing is I'm taking 1,000 and I'm dividing it by 100 to the 3rd power. 100 is 10 to the 2 power, and then 100 to the 3rd power is 10 to the 2 raised to the 3 power, which is 10 to the 6 power. 1,000 is 10 to the 3rd power, so 10 to the 3rd divided by 10 to the 6 would be 10 to the -3. And I'd already have, in fact, 10 to the -3 kilograms per cubic centimeter or something like that. So what we can see now is I've now canceled out the cubic meters, and I've now got it in kilograms per cubic centimeter. And obviously that's going to be a potentially big number, but I want it in kilograms per liter. So what I know, as I wrote above, 1 liter is 1,000 cubic centimeters. So I'm now going to say, well, now that I have cubic centimeters in the bottom, I can say, oops, I don't need that color. I can say that 1,000 0.00 centimeters cubed is equal to 1.00000 liters. And now what you see is I have 1,000 times 1,000 on top. That's 10 to the 6, because it's 10 to the 3rd times 10 to the 3rd, which would be 10 to the 6. And then I have 100, which is 10 to the 2 raised to the 3rd power, which is 10 to the 6 on the bottom. So in fact, I finally get 1.00000, and that is kilograms per liter. So I think you can see the density of water is a really nice number. It's like 1,000 or 1, just about everything you want. So we've now done part C. What I'd like to do next is part D. In part D, we have to switch over to the British system of units, which is kind of a pain, but we shall do it. So let's go to D. And what I claimed, of course, was in pounds per cubic foot. I said I thought I recalled that the density of water was 62.4, but in this case, we're looking for pounds per gallon. I can do both. I'm going to go ahead and run through pounds per cubic foot as well. But in pounds per gallon, what I'm going to do is I'm going to say the density of water is equal to 1.00000 grams per cubic centimeter. And then I'm going to convert that by saying that there's 2.54 centimeters in each inch. And that's exactly, remember. So if I cube that, that's actually going to get rid of my centimeters cubed and leave inches cubed. And I can also convert that gram to a kilogram. And the way I do that is I say that, in fact, there's 1,000 grams in 1 kilogram. And the reason why I'm going to kilogram is because I happen to know a conversion between kilograms and pounds. So now I can cancel out this G here, and now I'm kilograms per cubic inches. I happen to know, again, a conversion factor between pounds and kilograms. You can look this up or you can derive it yourself, whatever you want to do. What it turns out is that 1 kilogram is essentially equal to 2.204623 pounds. So now we can say I've gotten rid of kilograms and I've gotten into cubic inches. So let's take just a second and figure out what this is, not because that's what they asked us, but because it's a nice break off point for the problem that I told you I was going to do extra, which is pounds per cubic foot. So what I'm going to do is I'll take 1, I'm going to multiply that by 2.54, and that's cubed. And then I'm going to multiply that by 2.204623. And then I'm going to divide that by 1,000, of course. And that's going to give me 0.0361273. And that's pounds per cubic inch. Let me expand on that a little bit because clearly that's kind of small. So this should be pounds per cubic inch. Okay. And I've got more digits. So now that I have that, I want to go ahead and break off for a second and do pounds per cubic foot. So 0.0361 27. So that's 2 pods of 3, even though I didn't space them. And then 2982. And that's pounds per inch cubed. Now what I'm going to do is say, okay, well, I know that I know that 12 inches is equal to 1 foot. And then I'm going to have to cube that, of course. And then that inch cube will cancel out with this inch cube. So I'm basically just going to take this number and multiply it by 12 times 12 times 12. And that gives me, it seems like I was right in my guess or in my memory, it is 62.42, let's call it 8 pounds per cubic foot for fresh water. Remember, I gave you the value for salt water was 64 something, but this is the value that I remembered from my scuba class, 62.42. Something like that. So we got that, but now I can also take from that 0.036 and go from cubic inches to cubic feet, because I happen to know the number of cubic feet, or excuse me, the number of cubic inches in a gallon. So again, the density of water is equal to 0.036 127 298, and then I'll leave a 2, and that's in pounds per cubic inch. I happen to know that there's 231 cubic inches in 1 gallon. So all I have to do is multiply that figure by 31. And I get 8.345 which probably is more than enough sig figs, and that is pounds per gallon. So the density of water in pounds per gallon is about 8.354. Okay. I've actually used these figures before, by the way. For instance, I own a pool, and if you need, for instance, to know how much chlorine to put in your pool, or how much soda ash, or sodium bicarb, or something like that, they'll often tell you a certain number of parts per million. So all that really means is the weight of the water versus the weight of the stuff you put in it. So if you want 3 parts per million, for every 1,000,000 pounds of water, you would want 3 pounds of, say, chlorine. So what you do is you take the chlorine container that you're using, powdered chlorine or whatever, see what its percent is, and then you take the percentage that it is, multiply that by the weight that you have. So for instance, if you have 70% cal hypo, you take 0.7 times 1 pound, that's 0.7 pounds, and then you divide that by the weight of the pool water. Well, if the pool has 18,000 gallons, you're going to multiply 18,000 gallons by 8.3454 to get the number of pounds. And then you're going to divide the 0.7 times the 1 pound by that 18,000 times 8.345. That'll give you a really, really small number. But then if you multiply it by a million, that'll be the number of parts per million. So this comes in handy in other ways as well. So I hope that helps you guys. I'd also like to give you one neat little thing that I found somewhat useful if you're messing around the British system. A teacher in middle school once pointed this out to me, asked me if I recognized it, and I was able, luckily, because I happen to know the facts, I was able to make it out to some extent. So I'm going to write something really weird here. It's going to be in blue. Okay, and I call it the G-man. And what you do is you can put a big O like that. Actually, those are too big. Okay, and they're not actually O's, they're Q's. So I'm starting to think that maybe you know what I'm talking about. And then inside of there, you can actually put a really large, let's go black this time, P. Okay, and then inside of each of the P's, of course, you can put a, let's go back to, ooh, let's go to green this time. That'll be fancy. I like green. We can go to a big C, big C, a big C, big C, big C. And it turns out that if you zoom in, say, on, well, that was not very dark, was it? Let's do a darker one. Let's do it gray like this. If I zoom in on this, what I will see is, in fact, a big C, inside of which is, and now I'm going to choose an even cooler color. I'm going to go with Carolina blue. And what we will get and these are, of course, ounces. And of course, they're units of volume, so they're fluid ounces. Like that. So this is something I just named the G-Man, but basically it allows you to figure out, that crazy system of units, the British system, which was basically made up historically based on certain things that were convenient, as opposed to reasoning and stuff like that, which is what the SI was. So you see the G, which is a gallon, obviously has 1, 2, 3, 4 Q's in it, so it must be 4 parts to the gallon. But you can also see that the gallon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 cups in it. So 16 cups obviously is a oops, I did something funny. 16 cups is obviously in a gallon. I just realized a cup is not supposed to be 8 ounces. That was a boo-boo on me. So let me fix that real quick. Zooming in here. Hopefully y'all caught that, but is a cup, is a cup 8 ounces? I'm trying to remember again. 16 ounces is obviously a pint, and a pint is 2 cups. Oh yeah, it is 8 ounces. My fault. I was good. Sorry about that. So I'll say 0, 0, 0, 0, 0, 0, 0, 0. So I was right. I apologize. Thought for a second there I got confused. But anyways, you can use that, and that's sort of the stuff you have to use. Like if you try to mix oil with gas for a weed eater, or for a leaf blower, or for an edger or something like that, they'll say 40 to 1 or 50 to 1. And what they mean by that is 50 parts gas to 1 part oil, or 40 parts gas to 1 part oil. Obviously, when you're talking about gallons, it turns out, as you can see from here, there's 128 ounces per gallon. That's what happened if you counted all the O's per 1 gallon. So if you wanted 50 to 1, what you'd want to do is take that 128 and divide it by 50, and that would be the number of ounces of oil you'd want to add to it. If you were doing 40 to 1, you'd divide the 128 by 40, which actually is a lot easier to do. But anyways, that would be the number of ounces of oil you'd want to add. So hopefully, I know I went way beyond what was required of me here, but I wanted to make sure you guys knew some extra details that might come in handy from time to time. So by all means, tell a friend about www.youtube.com/Billy Younger Physics Solutions, with just the B, the Y, the P, and the first S in solutions capitalized, and hopefully that'll help you. Have a good day.